to the computer, because if I do it to the cloud, I'd have to wait an hour for it to download, and I don't feel like doing that. So, ladies and gentlemen, let's begin multiple quantifiers. So as we saw last time, right, we discussed the universal quantifier and the existential quantifier. And we've got both of those here. So this is a single statement with both now included. So we've got for all some value of x that is in the domain D. Okay, here we go. Hold on just 1 second. All right, so where was I? So I was saying for all x that is an element of D, there exists a y that's an element of E, such that we get some other thing out of it, which is called P here. And it's got P of xy because typically it's got to be some kind of combination of the two things. Notice that there exists, or the existential quantifier always is followed up by such that, regardless if it comes first or second in the statement. Then when we negate them, it's actually very straightforward. Any for all turns into existential. All right, and then we get such that, then we take the existential, or there exists, it becomes the universal, and we also negate whatever the final part of the statement is. And that works regardless of what you start with. So at least this is pretty intuitive as in terms of how to do it. So let's go ahead and write a few of these. So it says write the statement in a sentence first. So we're given there exists and it's an element of real numbers. So there exists, we can say at least one real number such that, right, we have to include that, for all real numbers we can say added to the first returns 0, or you could say yields 0. You could specifically say there exists at least one real number x such that for all real numbers y. And then you could also say for the last part of the statement, let's see, what's the term I want to use here? X and y are opposites is one way we can say that. That's actually going to come up later. Right, if you add x and y and they return 0, that means that one has to be positive, one has to be negative. So that's another way you can say it. Any questions about that one? Or, well, I guess I should probably kind of not ask that question as much. So if you have a question, just go ahead and throw it in the chat and I will get to it as soon as I can. Unfortunately, we have to pause yet again. All right, so the next one, it starts off with the universal quantifier. So that's for all. I don't know why it always underlines this. For all. And then we've got for all integers, right? Z stands for integers. So all integers x, there exists, and we'll say an integer y such that x divided by y is not an integer. Another way you could say that, right, because I was talking to someone the other day, right, and how often do we say stuff like for all and there exists, right? So another way you could say something like this would be every integer x divided by a particular integer y does not yield an integer. So it's another way that you could say something like that. So hopefully that exercise wasn't too terrible. The next thing is changing a sentence into multiple quantifiers. And then after that, the next logical step is to work on the negation. So let's turn these guys into multiple quantifiers. So every real number has an opposite. So every real, kind of the same thing as for all. So I need that guy. So for all, and I'll say x that is, actually let me go see if I can grab the other e. There's a better representation than what I've been using for element of. So it doesn't really look like epsilon. It should be more of a, should more like this thing here, the other direction. So many symbols. Come on, where is this thing? Dang it. I didn't see it, unfortunately. So I guess I'm just going to have to use the symbol I already had. I just wasted 2 minutes looking for a symbol. There's another one, but the wrong direction. Oh well, tired of looking for it. All right. So every real number has an opposite. So for all x that is an element of reals, then we have to say.
I mean, you can just copy the symbol up there on the second statement.
You would think that, but it's in math type. And so I haven't been using math type because not all of you have it.
Oh.
But if you want to type stuff up, it's great. I would suggest downloading it. You could go to Google and download math type, and you see up here, I've got that as something on my ribbon. And it's a lot easier than using the equation editor or any of those things. So for all x, it's an element of the reals. It says has an opposite. Well, we have to say, okay, well, we've got multiple quantifiers. So what is the other value? Well, we have to say then that there exists another element such that, now it says has an opposite. So as you remember up here, right, x plus y equals 0 represents opposite. So that's how we can write it down here. So x plus y equals 0.
Should it say y is in the set R since it doesn't technically say that in the sentence?
It doesn't give you that necessarily in the sentence. So you have to kind of finagle that part of it a little bit. So if one of them is an integer, then you can assume, if not specifically stated, the other must be an integer, or sorry, a real number here. That's one of the main problems with a lot of these is they tell you to write it as a multiple quantifier, but it only seems to give you one thing. So it's a little confusing. Now, this one actually does have two things. It says some dogs do not like treats. So it should be pretty easy to pick out the dogs part, right? So some dogs means there exists, and we can use D if you like, D that's an element of dogs. Now the question is, what's the next part? So it's actually going to be treats, right? Some dogs do not like treats. So the next element is for all I just used Y, but I don't know, maybe we can use T this time. Since it's treats, so T is an element of treats. So there exists dogs such that for all treats, the I want to say where D does not like T. So that one's not a mathematical thing, so it's a little strange in terms of, what do I put for the last part? So let's read it again. It says there exists at least one dog, right? That's what it says, such that I don't care what kind of treat you choose, right? All treats where the dog will not like the treat. And that's what the sentence says, right? Some dogs do not like treats. So I'll leave that there in case you guys want to continue looking at that one. So as I said, the next logical step is for them to ask us to negate the sentences. So here we're asked to negate the multiple quantifiers. And remember that all that requires of us is to change the quantifiers and negate the final part of the statement. So instead of for all, we would change to there exists an X that is an element of I. Now, I stands for irrational numbers. Okay, so far we've learned R is for reals, Z is for integers, I is irrational, Q, which you see there at the end of this problem, is rational. Don't ask me why they chose Q, maybe for quotient. And I is a little tricky too because that makes you think integer, but it's irrational. So just the negation so far is there exists X that is an irrational number such that, right, we always need that following the existential statement. Then it's for all, right, because this existential right here has to become for all Y that is an element of irrationals. X, Y, the multiplication of those two elements, is now not a rational number. So I believe I will have to use math type for this one. So you guys can see this. It's pretty nice. Symbols, there is my not element of. The strange thing is to put it into Word, you have to close it and then hit yes. So XY is an element, not an element of Q. And make sure I put my comma in the right place. So we started with this. And yeah, just after that guy. So I hope that that's, fairly intuitive, that you just change everything, right? That's all we have to do here for a negation. Would someone like to try this one? I think I can give control to someone. If you want to try it, give me a little thumbs up on your screen, I guess.
I can try.
All right, so let me, let's see, remote control. There you go. So you should be able to type and go up to insert for the symbols. Yep. So you're changing the existential to the universal, so that's good. Okay. X is an element of reals. There exists Y that's an element of of rationals such that so here you're going to need to go to math type. It's a little farther over. There you go. And do inline. Yep. And then if you look across the top bar there, it's the 7th one over. Sorry, the here. Let's see, can I see? Yeah, right here. Do you still have control? Maybe it didn't show you my cursor. So you've got two rows of all these symbols you can use. The first, or sorry, two rows. In the first row, the 7th option over, or yeah, 7th one. Do you see it? Would you like me just to do this one? You know what the symbol is. It's just a matter of finding it. So it's just right here. And then all you got to do is close this out and hit yes. Okay. All right. And then get rid of that period, and we have to decide where does our comma go. I believe it's going to go after the for all statement. So let's just scroll up and check. So notice it's for all, comma, such that we get negation of the final part of the statement. So yep, just right there. Fantastic. All right. So let me go ahead and that was a weird way to put it. Abort control. So thank you for that one. Any questions so far, guys? Feel free to throw it in the chat. Before we do this, let me just write is not here to make this simpler. All right. So we've got two more things to learn so far today. We've got the forms here of universal modus ponens and universal modus tollens. And then we get to use some Venn diagrams to discuss whether things are valid or invalid. So our challenge here is to change the sentences into a form that we recognize. And by that I mean into the for all, P implies Q, and then what it's given after it. Now, these are not the only two that we have here, unfortunately. I will tell you the other two types, and I need to see if I can find a chart maybe in the textbook that has all these, and then I can make a nice chart for you to use. So let's start with the first one. It says if a number is negative, then its cube is negative. So that's pretty clearly an if-then statement, right? And it says the first thing is a number is negative, and the second is its cube is negative. So we can say P of X equals negative number. Q of X equals cube of, sorry, I guess I should say negative cubed number. Or negative cube, because it says the cube of the original number is also negative. So this is a negative cube. And then the next part says X is a particular negative number. So if we look above, notice in these modus ponens and modus tollens, the second step says instead of P of X, we've got P of A. So remember, X is some element of numbers, right? Some integers, rationals, irrationals, whatever. So the next part says, okay, well, I'm going to pick a particular one and plug it in. So that's why this says X is a particular negative number. Therefore, X cubed is negative. Okay, so let's break this down. So obviously, even though it's P implies Q, because we're in the quantifier section, right, we have to start with some for all, right? So for all, and we'll say, I don't know, maybe Y this time, because X is the particular one, not the thing we're plugging in. Or maybe I could just change this to A. We'll make this A, and that'll fix our problem. So for all X, it gives us P of X. I need an arrow. Yeah, we'll just do that. P of X implies Q of X. The next part of the statement says A is a particular negative number. Well, P of X is some negative value, some negative number. So this is P of A. Cool. Sorry about that. Then the conclusion says, I guess I'm going to need math type, or therefore, A cubed is negative. So that's Q of A. So in fact, this is in the form of universal modus ponens. And if that's the case, then we can say it is valid. So let's try this second one. I think it'll make more sense, at least how to write it out this time, since we've just looked at that previous one. So it says, if a polyhedron has 4 sides, then the sum of the angles must be 360 degrees. So that is saying first off, we need for all. So for all x, that is some shape, then p of x is going to be a polyhedron. And of course, it's going to go down there. So P of X is going to be polyhedron of four sides, or sorry, yeah, four sides. Really? When I hit tab, it goes all the way over there. Okay, that's P of X. Q of X is going to be sum of angles is 360. So the first statement says if P of X, then Q of X, right? Everybody agrees with that. The next sentence says the sum of the angles of a particular polyhedron S is 360 degrees. Now that is the Q statement with a particular value plugged in. So that is Q of S. And then the last part, therefore, S has four sides. Now that is the P function, right? Polyhedron of four sides of a particular thing, S. So unfortunately, that does not match modus ponens or modus tollens. This is, however, referred to as converse error. And hopefully the word error instills the idea that it is invalid. Now 3 here is probably the most challenging one because it doesn't give us a whole lot. Right, it says all insects are small, dogs are not small, dogs are not insects. So we've got to come up with a statement for that. So let me find where I did this yesterday. The computer will load it. So I want to make sure I do it 100% correctly. Alrighty. So this one we have to interpret differently. So to do that, all right, so read the sentence. It says, all insects are small. So what that really means is if I pick an animal that is small, we can imply that it's an insect. Because every single insect is small.
Wouldn't saying all small animals are insects and all insects are small be two different things, though?
So the way it's written, right, what I'm trying to get at is the, if you read it the way it's written directly, you would be inclined to say P of X is insects and Q of X is small. But it's actually the other way around. It'll make more sense when we do the next one. Maybe let's go back and let's do 4 first. So let's look at this one. It says all rational numbers are real numbers. So that means if I pick a real number, it implies that it can be rational. Not that if I pick a rational number, that it has to be a real number. So again, it's counterintuitive on this one. So I'm going to say P of X equals real numbers. Q of X is rational. So let me write out the statement form here. So for all X, we have, again, P of X implies Q of X. The second statement says 2i plus 5, which is some particular value X, is not rational. Right, and we should know that. So if that number is not rational, then we get, where's the tilde? Not Q of X. Then the last part says, therefore, 2i plus 5 is not real. Okay, is not real is not P. That is exactly the format for modus tollens. And I should have, instead of X here, I should have, technically it's 2i plus 5 for each one of these. Okay, so that's universal modus tollens, and that is valid. So if we use that same rationale for the previous one, then we are saying P of X is small and Q of X is insects. Then the statement form over here is for all okay, good. For all X, we have P of X implies Q of X. Right, then it says dogs, which is so for before X is a particular animal, right? So dogs are not small, so that's not P dogs. And the last statement says, therefore, dogs are not insects. So that's not Q of X or of dogs specifically. And that, again, unfortunately, is not one that we have above. That one is called inverse error. And therefore is so this is also a good opportunity to say, you know, when we read these statements, it says all insects are small, dogs are not small, therefore dogs are not insects. And you think to yourself, yeah, that's true. Dogs are not insects. However, you can't take the validity of an outcome by real world knowledge. You have to test the argument. So what I'm trying to say is, don't get caught up with, oh yeah, that makes sense with the, you know, with a particular statement or the final outcome. You still have to test it logically. So I've seen a lot of people get wrapped up in, well, that, you know, well, clearly what was said there doesn't make any sense, so therefore it's invalid. But it might be a logical argument. So got to be careful with that. And I agree, 3 and 4 are very, like I said, counterintuitive. They don't seem to make complete sense in terms of how you have to put it together. So I'll probably give you, you know, maybe one problem of that, say, on your test. And it certainly won't be something this strange. All right, these I think are way easier to understand. This is a way of testing these arguments using Venn diagrams. And I tried to get all cute the other day and use the symbols on here, and it just got ugly. So I'll use the symbols, but I'll have to write in by hand. So let's read these statements. And for each statement, we're going to create a diagram. So the first one says, all teachers make mistakes, which means that in all of the mistakes, there is a subgroup that involves teachers. So this big circle is mistakes. And in here is teachers. Because the statement says all teachers make mistakes. The next statement says gods never make mistakes. So we've got the mistakes circle again. And I'm going to use a dot to represent gods. Although I think a circle is fine as well. Typically, I would use a dot if it's a subgroup of teachers. So let's just go ahead and use another circle. But you may do either. So statement 1, all teachers make mistakes. Statement 2, gods never make mistakes. The conclusion says, then teachers are not gods. So if we put the two things together, then now we've got mistakes. We've got teachers inside there. And now here we've got our deities. So, is it true? It says teachers are not gods. Well, if we look at that combined diagram, it's clear that teachers are not gods. So, true. All right, the second one here says all polynomial functions are continuous. So if this thing is polynomial functions, then I'm sorry, darn it, I put the wrong thing there. This is continuous, right? Because all polynomial functions must lie inside of the continuous functions. So this is polynomial. The next part says 1 over x is not continuous. Okay, well, that means it has to lie outside of continuous. And we don't have to always do each case. We can just put it all together now. So we've got continuous and polynomial. And then outside, we've got a very specific function, 1 over x, that is not continuous. Now the conclusion states, therefore, 1 over x is not a polynomial function. Is that true? Well, it can't be inside the continuous circle, and it has to be in there to be a polynomial function. Therefore, 1 over x is not a polynomial function. And this is also true. So can you guys give me a thumbs up if that made sense, please? All right, so most, if not all, said that was good. Okay. These are slightly different. So let's check those out. So the first one here says all students eventually study. Okay, so that means that within the realm of studying, right, all students must fall in there. So this is study, and this is students. Now it says this gentleman named Chris will eventually study. Okay. Therefore, Chris is a student. Now, you might make the assumption immediately when they say someone's name that they are a student. But does this person, Chris, have to be a student?
Nope.
He doesn't. So there's actually two options here. There's one where Chris studies, right? Because it tells us he will study, but he's outside of the students. He just walked in off the street and decided to study physics or mathematics. There's another situation where he goes ahead and signs up for a class, and now he is a student. So, can we conclude that he is a student? We can't, because we have two situations. We have an option where he is and an option where he is not. So that is false. And then number 4 here, this is my favorite one. And I can't remember if I was at this game or just watched it on television. And I don't know how many of you might be Orioles fans, but there was a day where the Red Sox player David Ortiz got so upset about striking out that he went into the dugout and beat the dugout phone to smithereens with a baseball bat. It was quite amusing to watch. So this says, no gentlemen smash phones with a bat. Okay. So how do I represent that? Somebody want to try this one? So I'll give you control here. Not so comfortable, I take it. All right. So I will do it. It says, no gentlemen smash phones with a bat. So that means we've got a category of gentlemen, which I will abbreviate as gents. And we've got another category that does not fall within that one. It has to be outside. And I'm going to abbreviate smash phones with a bat as SPWB. WB. Now, the next statement says David Ortiz is not a gentleman. Well, within the scheme of things here, all we know is he doesn't fall within this first circle. He could be out here. Or he could fall within the area of people that smash bats. All right, so we still have gents here. We're told he's not a gentleman, so he can't go inside there, but we're not told anything about whether he smashes phones with bats. So he could fall within here. So again, we've got two situations. We've got this one and we've got the one below. So can we conclude that David Ortiz smashes phones with a bat? So again, we cannot, right? So this is also false. So that is all that I had for you today. So I'm going to go ahead and stop recording.